Hello, I'm Dhruv Karnakaran,
And I'm Tiffany Zong.
and this is our Project 6, Collisions Between Disks video demonstration. In this video, we'll be talking about our project, our implementation, and why this is important. Now, to begin, here's our project. We have two disks, one blue disk and one red disk. We can control both the positions, the radius, and thereby the size of the disk, as well as the velocities, as you can see here. Now what we also show is one blue disk and one red disk that are slightly transparent. These are the disks at point of collision. And we can also show what the final velocities of disks are after collision. What happens, and if we press A, our animate button, we will see this in action. Now, our collision is working based off of the physics behind the collisions using the mass, which is defined by the area of the circle. And now in our next segment, Tiffany Zhang will talk about how we implemented the collisions between the two disks.
In order to find the time when the when the two objects collide, we want to find the time when the distance between the two centers of the object is equal to the sum of their radiuses. Because at that point, then the edges of the object the circles are touching. So in order to do that, we need to find a few vectors, which are the vector from the center of one object to the center of the other one, and we find the velocity of the objects subtracted from each other, v2 minus v1. And when we plug those into the equation and then square both sides, we end up with a quadratic equation which has a lot of dot products in it. And in that quadratic equation, we have the three coefficients, A, which is basically the velocity difference, v2 minus v1 squared, or dot product against itself. We have B, which is 2 times the vector from between the centers times the velocity difference. And we have C, which is the vector between the centers squared minus the distance, which is the sum of the two radiuses of the circles. So when we solve, we can plug in that equation into a quadratic formula, which is negative b plus or minus b squared, plus or minus square root of b squared minus 4ac all over 2a. And from that equation, we want to use the minus square root so that we can get the smallest time when they collide. And we know that if b squared minus 4ac is negative, that we have an imaginary root, which means the circles never collide.
So, we've described when the two disks collide, their behavior, but we also want to talk about what their velocities are after collision. Now, as you can see, when we have two equal disks with equal velocities opposing each other, they adopt the same velocity. However, when we have a disk that is perhaps bigger than the other, we want that to affect what the velocity is. And in this demonstration, we're using area as a stand-in for mass. So by using the principles of conservation of physical energy and conservation of momentum, we can take a look at how we can solve for the new velocities after collision. So what we want to do is we want to find a normal vector to the C1, C2 positions at collision, which is our collision vector across the collision. We want to incorporate that into a delta, which is the velocities combined times dot product with the n, scaled to the n vector. And then what we want to do is we want to plug that into v1 final and v2 using this formula right here. We're using the masses, in this case the area of each circle, which is pi r squared, to compute what the final velocities of the two circles are. As you can see, this circle moves slower after collision. This circle moves a lot faster because the velocity of this one is canceling out the velocity of this one's velocity. And this one's velocity is overseeding what this circle's velocity is. And so in a sense, we have an elastic collision. As a side note, I want to remember that elastic collisions are where physical energy is conserved and momentum is conserved because there is no loss of energy due to compression between the disks. Now Tiffany will talk about why this is important.
So we could have solved for the collision detection just by iterating the time each time in a loop and like adding 0.1 to the time each time and increasing the position of the circle and finding the point when the distances of the circles all at approximately when the radiuses, the sum of the radiuses. But the problem with that is that that's imprecise because you have a specific time increment in your program and you'll never actually hit the exact time when the circles are colliding. So that's why it's important to use physics so that we can solve for the time, and then we can check if the program has hit the time when the circles collide exactly, and we can take the leftover time and add that to the movement after the collision velocity.
Alright, this has been our video about collisions in our Project 6. Thank you.